In this lecture, we are going to look at how to perform statistical inferences when we are looking at multivariate means. In the previous lecture, we looked at quadratic forms of normal variates, and before that we looked at ways in which the estimators of the multivariate normal model behaves in terms of the mu vector, or rather x bar, and the sigma matrix, or rather, let's say, the sample covariance structure such as S. And we saw that they also have their own specific types of sampling distributions, and this leads us on the path to find a way, or at least training our mind, to think how we can potentially find ways to perform inferences when we want to test hypotheses. So that is what we're going to be doing today. Our objectives for today is number one, to understand, motivate, and argue around concepts of something called Hotelling's statistic. Number two, we're going to understand, prove, and give theorem 22. That is a mistake on my part. We are not proving theorem 22. I will spare you the proof of theorem 22. For those of you continuing with honors in our department, we do that at honors level. So we have to understand and give theorem 22. Number three, you have to understand, describe, and use Hotelling's statistic for inferences of multivariate means. And then you must be able to implement these concepts in computational software, understand the output, and can reach scientifically statistical conclusions regarding these specific hypotheses. Now, in the past, we've used the t-test when we want to perform a hypothesis that looks like mu equal to some mu naught, when my data, in that case, not a data matrix per se, but my data in the univariate case came from a normal distribution. We had the t-test and we had specific examples of when we would be using it, when we assume that we have the population variance, or when we use the sample variance. So what we want to do now is when we have a multivariate environment, and by multivariate I mean if we're looking specifically at a vector of values for more than one variable. And I want to test all of these to be equal to some pre-specified vector, let's call that mu naught, and I want to see what my inference will tell me from this. So we've seen this before in the t-test environment, but now we're going to look at the multivariate environment. And I want to encourage you to take time to revise chapter 12 from Bain and Engelhardt. I give you the page numbers there, which will be very useful in understanding and just a good refresher in terms of hypothesis testing in general. So, there is some statistic here involved. We've mentioned it in the previous lecture. I've mentioned it in the objectives, something we call Hotelling's statistic. Now, Hotelling was a very smart man many years ago, Harold Hotelling, and he found or devised this way in which we can kind of reach an inferential setting when we look at the multivariate normal environment. So let's look at theorem 22. Theorem 22. Suppose that y, which is again a vector, which is multivariately normal distributed with a mean vector of 0 and sigma as a covariance structure, and this is independent of a, which is also some kind of multivariate normal environment specifically, and all of these things are independent. Then we look specifically at this form. When I say this form, I'm going to take that out for a minute. We're going to look specifically at something called t squared divided by n minus 1 is equal to y transpose A inverse y. Now, this is not as much of a theorem, at least in our course, as it is actually just a definition. Because we don't really prove it here, you can just assume that this is true. So this is technically a definition. We build a statistic. We call this statistic t squared divided by n minus 1. And this emanates from this independent components of y and a. And specifically in the sense that we connect it via y transpose A inverse y. Now, I want to make sure that you don't miss out on any interesting things. So just take a note there. I did write it next to it. that is actually a quadratic form of sorts, right? Is it? Go and have a look again when you revise the previous lecture when we do discuss quadratic forms. So if this is my statistic, this is a statistic we saw already in Bain and Engelhard, if I recall, I think it's chapter 6 or chapter 9, somewhere in Bain and Engelhard at second year level. A statistic is a function from our random variates. So if this is a function y transpose A inverse y, then whatever we're left with is a function of my data matrix. In this case, it's t squared divided by n minus 1. Then t squared divided by n minus 1 multiply with n minus p divided by p, this whole chunk of thing. This will follow an F distribution with degrees of freedom p and n minus p. Now, note that I specifically circle t squared divided by n minus 1 and I did circle t squared divided by n minus 1 here as well, because this t squared divided by n minus 1 is specifically known as Hoteling's t squared statistic. If I ask you to give this to me somewhere in your life and you give me t squared divided by n minus 1 multiplied by n minus p divided by p, that is not Hoteling's t squared. Hoteling's t squared is t squared divided by n minus 1. And this is the statistic that we will be using when we are now going to be looking at our inferences of multivariate means. As mentioned, this is slightly more of a definition in our case. It is a proof, theoretically or technically, because there is a proof and a theorem, of course, but we do not consider the proof in our case. When we look at remark 13, I mentioned to you to take care to distinguish between the statistic t squared n minus 1 and t squared over n minus 1 times n minus p over p. The former, when I say former, I mean this one, is a function of the random variable y, and therefore it is a statistic. The latter, and that one, is a scaled version of the statistic, which is proved to follow an F distribution. Prove how? We don't consider it here, so don't have sleepless nights over it. And this is useful because we want to go and do significance testing, hypothesis testing. But to do this, we need to have some kind of insight into the probabilistic inner workings of this value. And so someone then went and said, oh, but you know what, guys, if you do this, if you multiply this with n minus p divided by p, then this thing has an F distribution. And that is useful because an F distribution, number one, is known, it's implementable, and it's analytically available if we need it. What do I mean by that? I mean, you can go into Microsoft Excel to calculate values from this distribution, critical values, p-values, etc., or in SAS, or in R, or in Python. So it's useful to have something known because we will be able to attach meaning to our hypothesis using this F distribution. Remark 14, I also mention, note in the above theorem that sigma is assumed to be known, specifically over here, that, if my pen wants to work, that sigma over there, we assume that it is known, right? And this is equivalent to assuming that the sample variance of a univariate sample, or at least the population variance actually, is known. When sigma is not known, we use something that can be estimated from the available data. We've seen now, how do we estimate sigma? How do we find, if I ask you in the middle of the night, how will you calculate that? Well, then that is some function of A, or which is some function of S, right? In this case, A and S are those cross products. We've seen this already in Theorem 22, right there at the top, where we see A is also just some function where we build a matrix from it. And we use that to estimate our sigma hat. Now you can ask me, Johan, why exactly is there f of A and the g of S? I just use that notation because we know that there is a bias problem and a bias correction when we do look at sigma. If you remember to page 18 of our notes in this course, there we see, for example, that we use n minus 1 times S, which is equal to A. But we will get to this in a little moment. So that function just means like, it's not sigma hat is equal to A. Sigma hat is equal to something of A, which is usually just a bias correction. So just take note of that. We're going to be looking specifically at the case where sigma is unknown. And now, if there's only one thing that you take from this entire video today, is that, not what I wanted to do, is that you do make a circle or a note or a block or something that we want to test a hypothesis where mu is equal to mu naught. Right, let's now make sure we understand what does mu mean and what does mu naught mean. Consider a random sample of n observations, n larger than p, from a multivariate normal distribution. Multivariate normal in this case means that there is my mu and this is that mu. It's where my data comes from. Now, we want to test this equal to some specific value, some pre-specified vector. There is a mean, of course, for x1. There's a mean for x2 because if you can recall, we know we write this mu. We can write it now as mu1, mu2. That's terrible. Mu2, blah, 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 up to mu p because that is my number of variables. So my mu naught will be a pre-specified when you guess, or your boss or your client or your colleague or someone comes and tell you, is that variable's average equal to 42? Then that mu1 might now in that instance be equal to 42. And the next one might be 374.1, blah, 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 some values. And we want to test, but from my data matrix, does this seem viable? Is mu1 equal to 42? Is it significantly different from 42 or not? So that is what we want to aim towards. But we have to do a little bit of mathematical juggling in order to understand the probabilistic undertones and how exactly Hotelling's t-squared fits into this. Right, in the second line, in this case, we know that root n x bar minus mu is multivariate normal. If you're unsure why this is true, I encourage you to please go back 2 lectures to the sampling distributions of x bar. Remember, in this case, don't miss the fact that I'm working with x bar specifically. Is normal 0 sigma independent of A? And where the z's are all independent? Let's hang on here for a little bit. I just want to highlight something specifically. Here we have the exact relations between A, which is equal to n minus 1s, which is equal to n sigma. So make sure, sometimes you have A, sometimes you have S, sometimes you have sigma hat. You don't know what your client or your boss or your previous co-worker that you took over from one day, what they were working with. And you need to know if you're working with large amounts of data, when you're working with a sample of a specific type of clients for a big insurer, and you need to go and see from all of their variables, house repayment and income and this and that. And you want to go and look at this huge data chunk, and you want to look at the covariance structure. There's ways of finding A, there's ways of finding S, and there's ways of finding sigma hat. And we need to be aware of the relationship between these. Otherwise, we will make a mistake inferentially, which means that you might cost your job a lot of money. And that is, I want to say in my experience, fortunately not in my experience, but that's never a good idea. So we can now go and we want to write our t square over n minus 1. We want to write our t square n minus 1 in terms of sample information. I want to know, how will I calculate this if Johan gives me a data matrix? If I come to you and I present you with a data matrix X, how exactly will you go and calculate t square? So these 3 lines gives us the specific relationship each time between A, sigma hat, and S. So writing out the steps, I'm going to leave this specifically to you. How do you get from here to here? And how do you get from here to here? I'm going to leave this to you. It's an extra 2 lines in between or something like that. It follows quite naturally, and you have to be aware of this correction for the bias that we do so often. This way that n over n minus 1 comes from, and there's just an n. So you have to be aware of exactly how those unbiasing factors also relate to Hotelling's t-squared statistic. Now in this case, we see here that if I look at my t squared, let's just look at this one for example, that expression. I see that my Hoteling's t squared is related to x bar, which is over there and there. It's related to mu naught over there and over there. And it's related to s. So immediately I can see from this expression that my whatever I'm going to use inference on, it's related to the mean. That makes sense though, right? It makes sense that this should have something to do with x bar because we're testing for the mean. So this is not incidental. It's not by accident that that x bar is there. If x bar wasn't in this expression, we wouldn't have gotten far. So that x bar is meaningful, number one. Number two, this mu naught is my pre-specified vector coming from my hypothesis. This is what I want to test it against. And then this S inverse encapsulates the covariance and the relationships between the variables, which I must also take into account. Now, I can ask you, okay, can you please go, not what I wanted to do, can you please go and calculate, this line for me in SAS or in R or in Excel even. Can you go and do it? Why, yes. You will know what mu naught is. I will give it to you, or you have to build mu naught yourself from the question. X bar, you can calculate. We've done it in the assignments. S, you can calculate. You can find the inverse of S. So you can go and physically calculate the value for Hoteling's t squared. You can go and calculate that. And then secondly, well, you will hopefully know how big is my sample and how many variables I'm looking at, which means you can directly go and calculate the function that we will be using that follows an F distribution. And so even though what I wrote here in the purple block over here, this guy, this is Hoteling's t squared statistic. This is what I need to make it a distribution or have it follow a distribution. This entire thing will be my test statistic. Like we had the z-score or the t-score in the past, this thing in the pink block is what we will call our test statistic. And this follows some distribution f, which we can use and find. So immediately, this is what I will be using in order to go and test my hypothesis, mu equal to mu naught. Okay. We reject H naught if this test statistic is larger than some pre-specified critical value. So this will be some critical value. And I assume that you will be able to calculate that because that comes from knowledge of previous years. And that is pretty much where our inference of the multivariate mean will rely on. One thing before we go and look at an example I want to mention to you is I want to write out here. I want to write out this t-square statistic. If I have t squared over n minus 1, then this is now I've seen is equal to n over n minus 1 x bar minus mu S inverse and x bar minus mu naught. Again, remember all of these are actually vectors and matrices. Correct. Now, if we just look at this expression, we have to think, well, what does this inference really mean? For me, at least, this makes sense. Thinking about it in the sense of the quadratic form. This is a quadratic form of sorts, so have a look out for that as well. But then most importantly, we're looking, in a sense, we are looking at the squared distance between x bar and mu naught. I want to see, are they far away from each other? Are they close to each other? So it means that if my hypothesis value, which is this mu naught, if this mu naught is close to my sample averages, it means that my Hoteling's statistic will be small, which means my test statistic, this one over here, will probably not be rejected, which means that mu is probably equal to what I posed in mu naught in the first place. So from a distance point of view, this does make sense. However, let's suppose mu naught is wildly different from x bar. This means that in the vector space, if we take this quadratic form, by quadratic form here, I mean if we take x minus mu naught transpose x minus mu naught, it means that that value will just get bigger because I'm just multiplying larger things with each other. And if I keep on multiplying larger things with each other, it means my test statistic, this one that I have over here, will just increase, which means it's not likely that x bar and mu naught are close, which means mu and mu naught doesn't seem like that is the right choice for mu naught. So that's one way of thinking about this, which I think makes it very intuitive. I have to mention though, just remember, we still have our sample covariance structure information built in here as well. I just pose this almost from a geometric kind of viewpoint when I just speak about x bar and mu naught. But of course, we are retaining this variance and covariance behavior between the variables as well within this expression. Now, exercise 3 is quite painless. Exercise 3 asks you to write down the alternative hypothesis. I'm not going to write this down per se. I want you to go and dream about it a little bit. What would be the alternative hypothesis? Is the alternative hypothesis the fact that mu is not equal to mu naught? Is that the alternative hypothesis? Is it something else? Don't know. Well, I know. I want you to go and think about it. Think. Basically, what I'm asking, all the variables averages could be posed closely in terms of mu naught, but one might be wildly different, which might, cause us to reject the null hypothesis. But does that then mean that mu is not equal to mu naught? Don't know. Go and have a think. We have a little example, which comes from a book by Seal in 1994. Here we observe the head length and the head width. So immediately we see here I have variable 1 and here I have variable 2. Of a sample of 49 frogs, of which 14 were male and 35 were female. In this case, the question to be answered, this is our main question for this example. Does the average for female frogs for both head length and head width differ significantly from 25? And then, so up to here is what will be given. What is also given here is we have our sample averages for male and female, and we have our estimates for the covariance structure for male and female. Just take a specific note. There's not supposed to be a space here. It's all one line. So here we have our indication of our covariance structure for the males, covariance structures for the females for these sample of frogs. Now, the question was, we have to consider the hypothesis that mu for the females are 25 and 25. This is for x1. This is for x2. Right. It's also always a nice idea to now just make a little note here. Mine won't be so little. But now to remind yourself, P is equal to 2. Immediately makes it clear. There's no ambiguity about this. And then also, the question was specifically regarding the female frogs. And there were 35 of them. So N is equal to 35. Why give you more information about the male frog? Well, maybe to confuse you or maybe just to give you all of the information. But the question will specifically or explicitly state it's for the female frogs specifically or whatever. All right. You can go and calculate the solution by hand because for this, we will be using Hoteling's t squared. There we go. We calculate this. Remember that this sigma is an inverse, and there we have the inverse. And we can go and calculate our value. We get 3.401. This 3.401 has to be translated into our test statistic, and we use it specifically over here. There is my test statistic, and my final test statistic value is equal to 56.116. I go and I find my value for the critical value. It's 5.312, something that is not stated, of course. Alpha in this case was 1%. It could be 5%, 10%, or whatever. So because this value, that value is larger than 5.312, we reject H0. This means at least one of the means differs significantly from 25. Just out of pure interest, when we look at this averages, sample averages, we see here there's one that's 22, this one's 24. Quite close in a sense to 25, which we want to measure. This one is a bit further from 25. Of course, that by itself is not really meaningful. It just helps us with understanding the problem, because we must not forget the role of the covariance structure in the expression as well. You can go and do this in Proc IML, and here you can immediately identify, there's my F statistic, there's my critical value, there was Houghton's value that we also calculated, and immediately we see our calculations by hand were correct. Just remember over here, this is sigma F hat, right? That's my estimate of the sample covariances. And we can calculate all of these. Next, one extra exercise I would really want you to go and do is to go and redo this exercise that we just looked at about the frogs. But now I'm asking you to go and test mu m equal to 19.5 and 20.5. And then testing mu m also 19.9 and 21. Is there a difference in the outcome? Comment and discuss. Go and do it by hand. Go also and do it by IML. You have the code for it. And immediately we will be able to see how sensitive is mu to these kind of changes. And that brings up some thoughts that we discussed in previous years as well about power of the test. How quickly will I be able to pick up departures from the null hypothesis? But for now, example 17 and then in example 18, there's a website that you can go have a look at. There's also additional examples and some relations that they make to the univariate environment.